In this video, we are continuing our look at organic molecules, and we are continuing to focus on bonding in organic molecules. So in our last video, we talked about valence bond theory and molecular orbital theory. So now let's apply valence bond theory to hydrocarbons. Let's start our look at hydrocarbons by focusing on the simplest hydrocarbon, which is methane, CH4. If we draw the Lewis structure, we have carbon connected to our 4 hydrogens. And in terms of shape, based on valence shell electron pair repulsion, we know that carbon connected to 4 groups is going to have a tetrahedral arrangement, so that we have the hydrogen, carbon, hydrogen in the plane of the paper, and then we have one hydrogen coming forward and one hydrogen going back behind the plane. Now, let's also think about hydrocarbons and let's apply valence bond theory. So the electron configuration of carbon is 1s2, 2s2, 2px1, 2py1. So if we think about our half-filled orbitals, we have a px, and let's say it's filled in down here, and a py like this. And we have one electron because these are half-filled orbitals. Next, if we look at the electron configuration of hydrogen, this is 1s1. So this is our orbital with one electron. So with valence bond theory, we have our half-filled orbitals and then we overlap them. So what is that going to look like? We would have our carbon with our p orbitals, and then we would have hydrogen overlapping here and another hydrogen overlapping here, because we had one electron from the p orbital of carbon and one electron from the hydrogen, one electron from the p orbital, one electron from the hydrogen. So this says that our molecule would be CH2 and it would have a bond angle of 90 degrees. So that's a problem, because this, which is predicted from valence bond theory, is not the same as this, which is what we predict from VSEPR. So there's a problem with one of these theories. Experiment shows that methane has a tetrahedral arrangement. So the problem then is with valence bond theory. So why did I waste your time talking about valence bond theory if it only works for hydrogen? There's got to be more to it. So if we try to apply valence bond theory to the simplest hydrocarbon, methane, we know that the electron configuration of carbon in an atom is 1s2, 2s2, 2px1, 2py1. But that's what got us into trouble. But we have to keep in mind that the electron configuration of carbon in a molecule is not necessarily the same. So let's think about the electron configuration of carbon in an atom, and we're just looking at the valence electrons. So this is our 2s orbital, and we have 2 electrons in here. These are our 2p orbitals, and we have 1 electron here and 1 electron here. But the electron configuration of carbon in a molecule is not necessarily the same. So it's possible that these orbitals, the s and the p orbitals, can combine or blend or hybridize. So if all 4 of these orbitals combine, then we get 4 new orbitals. So they will be the same energy as each other, and these are called sp3. Because they are made up of the blending or the hybridization of 1 s orbital and 3 p orbitals. So sp3 hybridized. Now we have to remember that we have 4 valence electrons. So if we fill in those valence electrons, we have 1, 2, 3, 4. So we have 4 half-filled orbitals, which means we can make 4 bonds. So as we look at bonding in hydrocarbons, we can apply valence bond theory as long as we include hybridization. So let's talk about the characteristics of our sp3 hybridized orbitals. So in terms of energy, they have the same energy as each other, and it is between the energy of an s and a p orbital. In terms of the shape and geometry, when you mathematically combine the s and the p's, what we get is something that looks like this with a little nub behind it. We are going to ignore this little nub, so our focus is this. And when we put all four of them together, what we get is one in this direction, one in this direction, one coming straight forward out of the plane, and one going back behind the plane. In other words, we have a tetrahedral arrangement. So if we think about a carbon with sp3 hybridization, then we're going to have an sp3 orbital, another sp3 orbital, another sp3 orbital, and another sp3 orbital, and each of these is filled with one electron. So when we consider bonding in methane, we have our carbon with the 4 sp3 hybridized orbitals, each filled with one electron. And then we have our hydrogen 1s, another hydrogen 1s, another hydrogen 1s, and another hydrogen 1s. In other words, we have CH4, and the carbon-hydrogen bonds take on a tetrahedral arrangement. So when we use valence bond theory, including hybridization, our prediction for methane agrees with experimental evidence. So as we continue to use sp3 hybridized orbitals, let's consider the bonding in ethane, which is CH3CH3. Well, each carbon is going to be sp3 hybridized. So I'm going to draw this a little bit tilted compared to how I drew it on the previous slide. So one of our sp3 orbitals goes like this, and then the other one is up here, and then here's the one that's coming forward, and here's the one that's going back. And this is half filled, half filled, half filled, and half filled. Sorry, those arrows are not very clear. They're meant to be a single barbed arrow representing one electron. Now, our second carbon atom that's sp3 hybridized will have an sp3 orbital, another sp3, another sp3, and another sp3 going back behind. And this one will have one electron, one electron, one electron, and one electron. In addition, we have our hydrogens, which have one electron in an s orbital. So as we think about the molecule altogether, we have this carbon will have its sp3 orbital overlapped with this carbon's sp3 orbital. So one of these electrons and one of these electrons will combine to form a bond. And now here is another sp3 orbital, an sp3 coming forward, an sp3 going back with one electron in each of these. And then here's our other sp3, our sp3 coming forward and our sp3 going back, half filled in each of these sp3 orbitals. This orbital is overlapped with this orbital, but the other orbitals can overlap with hydrogens. So here's our hydrogen, here's a hydrogen, here's a hydrogen, here's a hydrogen, another hydrogen, and another hydrogen. In other words, we have a carbon-carbon single bond. These carbons are each connected to a hydrogen and another hydrogen and another hydrogen. Each carbon is tetrahedral, and as we think about the formation of these bonds, what we're looking at here is a carbon sp3 overlapped with a hydrogen s orbital, and that's the same for this carbon-hydrogen bond, this one, this one, this one, and this one. And then this bond is made up of a carbon sp3 overlapped with another carbon sp3 orbital. All of these are sigma bonds. So we can use valence bond theory with hybridization to explain the bonding in hydrocarbons. In particular, whenever we have carbon connected to 4 groups, then that carbon can be sp3 hybridized.